In the last 7 days, more than 500 tremors struck the west coast of North America in a single snapshot, and roughly 1,900 across the week, the highest count in about 30 days. Not one of them was felt. And that is exactly what should concern you, because those tremors mark the most dangerous fault in the United States, quietly loading toward failure. Tonight, I will show you what that surge means, why monster earthquakes are multiplying worldwide at the same time, and whether the giant sunspot turning to face Earth has anything to do with it. Buried beneath the west coast of North America, sensitive instruments spent this past week recording more than 500 small bursts of motion in a single snapshot. And across the full 7 days, the count climbed to roughly 1,900. None of them were felt. Not one of them shook a single picture frame off a single wall. And that is exactly why they matter. These were not earthquakes in the way you normally think about earthquakes. They were something quieter, something further down, and in many ways, something more unsettling, because what they are telling us is that the most dangerous fault system in the United States has been busy doing the one thing it does in the years before it finally breaks. The activity is concentrated along the southern end of the Cascadia Subduction Zone. That is the roughly 1,000-kilometer megathrust where the Juan de Fuca plate is being shoved underneath the North American plate, running from Northern California up through Oregon and Washington and into British Columbia. This is the fault that produces the largest earthquakes on the continent. And over the past week, the southern portion of it lit up with a surge of what scientists call tremor, the highest count anyone has logged in about 30 days, with the activity climbing sharply right around the start of the week. Most of those signals clustered beneath Northern California in the southern Cascadia margin, far down on the plate interface, roughly 60 kilometers below the surface, which is about 40 miles straight down. There was a second, smaller cluster underneath the Seattle area, and while the public went about its week with no idea any of this was happening, the people who watch these maps for a living were paying very close attention because a week like this is the fault talking. The question is what it is saying. Let me explain what tremor is, because once you understand it, the rest of this story snaps into focus. When you picture an earthquake, you picture a sudden, violent jolt. A fault that has been stuck for decades or centuries finally slips all at once, and the ground heaves. Tremor is the opposite of that. Tremor is the sound of the lower part of the fault, slipping slowly, quietly, over hours and days, without ever producing a sharp jolt. It is not volcanic. It is not magma moving. It is rock grinding against rock so gently that it never registers as a felt earthquake at the surface. It shows up only as a faint, sustained rumble on sensitive instruments. Here's the key. A subduction fault like Cascadia is not the same all the way down. The lower portion, far below the surface, is hot and under enormous pressure, and down there the rock behaves in a more ductile way. It can creep, it can slip slowly. That is the part that produces tremor. But the shallower portion, closer to the surface, is colder and more brittle, and that part is locked. It is jammed shut. It is not moving at all. And because it is not moving while the plates keep pushing, it is storing energy year after year, like a spring that is being wound tighter and tighter and never allowed to release. So when you see a surge of tremor on the lower part of the fault, you are watching the lower section slip. And every time that lower section slips, it transfers a little more stress upward onto that locked, brittle energy storing zone above it. The tremor itself is harmless. What the tremor does to the locked zone above it is the entire reason seismologists lose sleep. The locked zone is the part of Cascadia that breaks in a great earthquake. It is the part that has not moved since the year 1700. And every slow slip episode, every week of elevated tremor like the one we just saw, nudges that locked zone a small step closer to failure. Think of it as a stress clock. Each tremor episode advances the clock by a tiny amount. It does not tell you the hour. It does not tell you the day. But it tells you, unambiguously, which direction time is moving. This is where I want to be careful with you, because there is a responsible way to talk about this and an irresponsible way. And the irresponsible way is everywhere online right now. An elevated tremor week does not mean a great earthquake is coming next week. Slow slip episodes happen on roughly regular cycles all along the fault, and the overwhelming majority of them come and go without a major quake following. They raise the probability of failure by a small amount. They do not schedule the event. Anyone telling you this surge means the big one is days away is selling you something. But here is the part that should still get your attention. The strain those tremors are loading onto the locked zone is real. It is measurable. It does not go away when the tremor stops. It accumulates. And the locked section of Cascadia has been accumulating it without a major release for longer than almost anyone watching truly appreciates. It helps to understand what that locked zone is capable of when it finally lets go, because the felt earthquakes most people have lived through give you no useful intuition for it. A great Cascadia rupture would not be a jolt. It would be shaking that lasts for several minutes, not several seconds, as the rupture tears along hundreds of kilometers of fault. The coastline would drop in places instantly, and within minutes of the shaking, a wall of water would come ashore along the Pacific Northwest coast. The same kind of tsunami that crossed the entire ocean and was recorded in Japan 3 centuries ago. This is not a regional inconvenience. It is the single largest natural disaster scenario in the continental United States, and the locked zone we are talking about is the exact piece of crust that would produce it. So when the lower fault slips and loads that zone a little more, the stakes behind that quiet, unfelt tremor are about as high as natural stakes get. To understand how long this has been building, you have to go back more than 3 centuries. The last time the full Cascadia margin ruptured was January of the year 1700. We know the date with remarkable precision, and the way we know it is one of the great detective stories in earth science. That earthquake, a magnitude around 9, sent a tsunami racing across the entire Pacific Ocean. It slammed into the coast of Japan with no local earthquake to explain it. Japanese officials wrote it down. They recorded the timing and the damage of a wave that arrived out of nowhere. Centuries later, scientists worked backward from those written Japanese records, matched them against the geologic evidence on the American coast, and pinned the rupture to a winter night in 1700. They call it the orphan tsunami, a wave with no parent that anyone in Japan could see. That was not a one-time event. The geologic record along the Pacific Northwest coast preserves the fingerprints of these great quakes going back thousands of years. Offshore, underwater landslides triggered by violent shaking leave distinct layers in the seafloor sediment. Onshore, you can find ancient forests that suddenly dropped below sea level and drowned, and buried sand layers left by tsunamis sweeping inland. Those drowned forests are worth pausing on because they are one of the clearest signatures a fault can leave. When the coast suddenly dropped during the 1700 earthquake, entire stands of living trees were pushed down into the salt water and killed where they stood. Their roots are still there today, preserved in the tidal mud, a row of ghost stumps marking the exact moment the ground fell. By matching the growth rings of those dead trees against living trees and other dated wood, scientists could narrow the death of those forests to a single year and even a single season. The earth wrote the date of its last great rupture into the wood itself, and we learned to read it. Layer by layer, tree by tree, this record shows roughly 20 earthquakes of magnitude, 8 or greater, along Cascadia in the last 4,000 years. Now do the arithmetic that the geology forces on you. The last full rupture was 326 years ago, and here is the number that stops people cold. That 326-year gap is the longest interval in the entire 4,000-year record. The next longest stretch anyone has documented was about 291 years. We are now living through the quietest, longest pause Cascadia has taken in 4,000 years. We have never watched it stay silent this long. I want to be precise about what that does and does not mean, because the word everyone reaches for is overdue, and that word causes more confusion than clarity. Cascadia is not a bus. It does not run on a timetable. The intervals between its great earthquakes are not evenly spaced. Some gaps in the record are a few centuries, some are much longer, and the variation is wide, so saying the fault is overdue, as if it has missed an appointment, is not how the science works. But here is the honest version, and it is more unsettling than the word overdue, not less. The strain accounting is real. The plates have not stopped moving. North America and the Juan de Fuca plate have been converging this entire time, every single year, locked against each other along that shallow zone, and none of that accumulated energy has been released in a great earthquake since 1700. So while no one can tell you the fault is due on a particular date, what they can tell you, with confidence, is that the amount of stored energy now sitting in that locked zone is enormous, and that it has been building without release for longer than at any point in the record we can read. The tremor surge this past week did not create that danger. It just reminded us, in real time, that the loading never stopped. And Cascadia is not even the only sleeping giant on this coast. While everyone fixes their attention on Cascadia and the Pacific Northwest, there's a second fault system to the south that has been silent in its own alarming way, and it runs through the most populated parts of California. The southern San Andreas has not produced a major rupture in well over 300 years. The last great earthquake on the section to the north was the Fort Tejon earthquake of 1857, a magnitude around 7.9. But the far southern branch of the San Andreas has been quiet even longer than that, with no modern record of the moderate, magnitude 6 or magnitude 7 earthquakes that would relieve some of the building stress. That silence is not comforting. It is the opposite of comforting. When a fault produces occasional moderate earthquakes, it bleeds off some of its accumulated stress in manageable installments. When a fault goes completely quiet for centuries, it is not resting, it is loading. And the longer it loads without release, the larger the eventual earthquake becomes, because there is simply more locked-up fault length available to break all at once. Most assessments now put the maximum magnitude for a southern San Andreas rupture near 8.1, which would be larger than the 1857 event, precisely because there is now more stored, unbroken fault to let go. So step back and look at the whole coast as one picture. To the north, Cascadia, silent longer than at any point in 4,000 years, capable of a magnitude 9. To the south, the southern San Andreas, silent for centuries, capable of a magnitude around 8.1. Two of the most dangerous fault systems on the continent, both far into the late stage of their cycles, both quietly loading at the same time. And that raises a question that scientists have only begun to take seriously in recent years. Could they break together, or one right after the other? This is the part of the story I want to label very clearly as speculative, because it sits at the edge of what the science can currently support. The idea is that these two great fault systems, which share the same broad plate boundary setting along the west coast, might be capable of rupturing in close succession, or might be dynamically linked in some way, so that a great earthquake on one could influence the other. This is not science fiction. There is a real line of research over the past several years exploring exactly this possibility. The physics by which one large earthquake can shift the stress on a neighboring fault is well established, and we will come back to that, because it is one of the most important and most misunderstood ideas in this entire story. But the specific scenario of a coupled Cascadia and San Andreas event is, for now, a low probability, high consequence possibility that researchers are studying. It is unconstrained in timing. No one can tell you it will happen, and no one can tell you it will not. What I can tell you is that the people who study these faults no longer dismiss the idea out of hand, and that alone tells you how seriously the loading on this coast is now taken. That is the core of the story. The West Coast is in a genuinely late stage of strain accumulation on two of its most dangerous fault systems, and a noisy week of tremor just made that buildup visible. But this week was not happening in isolation, because while the West Coast was quietly loading, the rest of the planet was doing something that grabbed a lot more headlines. Over roughly the same stretch of days, large earthquakes lit up across the globe, and online the word that kept appearing was that the planet itself seemed to be ringing. Let me give you the confirmed events first, because that is where this has to start. West-southwest of Sarangani in the Philippines, a magnitude 6.5 struck at a depth of about 42 kilometers, which is roughly 26 miles down. In the Hindu Kush, near Jurm in Afghanistan, a magnitude 6.1 hit, but this one was very far down, around 200 kilometers below the surface, which is about 124 miles down. A quake that far down is widely felt across a huge region, but tends to do limited damage at the surface, precisely because all that rock between the rupture and the cities above absorbs the energy. Those were not the only ones. There was a run of very far down earthquakes scattered across the western Pacific. A magnitude to 5.9 in the Timor-Leste region, more than 500 kilometers down. A magnitude 5.9 in the Banda Sea. A magnitude 4.5 near Fiji at a stunning depth of more than 500 kilometers. And a magnitude 5.7 in eastern Honshu, Japan. On top of that, the seismic watch community pointed to what looked like roughly 2 magnitude 7 events and 2 magnitude 6 events within a single week, several of them clustered on the same day. I want to flag that carefully. The 2 magnitude 7 figures are community framing, and you should treat them as reported context rather than confirmed, while the Philippines and Afghanistan events are solidly confirmed. It is worth separating 2 very different kinds of earthquake hiding in that list, because lumping them together is part of what makes a week like this feel apocalyptic when it is not. Several of those events ruptured far below the surface, the ones in Afghanistan, Timor, the Banda Sea, and near Fiji, breaking 200 to more than 500 kilometers down. Those happen inside the slabs of old ocean floor that have been dragged far down into the planet's interior, and the physics that far below is genuinely different from a shallow quake. They are felt across enormous areas because the energy radiates up through a huge volume of rock, but they rarely cause the kind of surface devastation a shallow quake of the same magnitude would. Compare that to the shallow megathrust activity loading the west coast, where the rupture happens close to the surface and close to where people live. Same news cycle, same scary magnitudes scrolling past on your screen, completely different threat. Telling them apart is the difference between understanding the planet and being frightened by it. And it kept going. In the Eastern Caribbean, there was an uptick, a magnitude 5.0 near the Dominican Republic and a magnitude 4.7 near Guadeloupe, with smaller swarms around them. That region has a violent history. The Guadeloupe and Lesser Antilles Subduction Zone produced an earthquake estimated near magnitude 8.5 back in 1843, about 183 years ago, and a magnitude 7.5 in 1974. In Pakistan, a sequence started with a magnitude 5.2 and topped out at a magnitude 5.4 near the same plate boundary, which some watchers raised as a possible foreshock pattern, though that is unconfirmed. Long, quiet interior fault systems in Nevada and even areas outside Las Vegas showed elevated activity. And up in Alaska, a magnitude 4.9 near Clam Gulch and a magnitude 4.2 closer to Anchorage struck along the Gulf of Alaska Subduction Zone, the same megathrust that produced the 1964 magnitude 9.2 Great Alaska Earthquake, the second largest quake ever recorded. So when people say the planet is ringing, you can see where the feeling comes from. But the feeling and the data are two different things. Here is the reality check, and it is important because the difference between feeling alarmed and being informed lies right here. Global earthquake rates are, statistically, fairly steady from year to year. The Earth produces a remarkably consistent number of large earthquakes annually. What varies is how they clump in time, and clumping is exactly what randomness looks like. If you flip a coin 100 times, you will get streaks of heads. Those streaks do not mean the coin has changed. They are simply what chance produces. A week with several large earthquakes scattered across different continents, on completely different fault systems with completely different mechanisms, is not evidence that the planet is destabilizing. It is, most of the time, evidence that we noticed, and our attention amplifies everything. We live in an era where a magnitude 6 in a remote region is on your phone within minutes, complete with a map and a depth and a dramatic headline. The earthquakes have always happened at roughly this rate. What is new is that we now see all of them, instantly, all at once, and our brains do what brains do, which is to assemble unrelated events into a story. So the honest version of monster earthquakes multiplying worldwide is not that the whole Earth is suddenly coming apart. The honest version is more specific and, in a way, more useful. Several particular named zones are individually late in their cycles right now. Southern Cascadia, the southern San Andreas, the Eastern Caribbean, parts of Pakistan, the Gulf of Alaska. Those are real identifiable concerns each on its own clock. Lumping them together into a single planetary event is where the science ends and the panic begins. And there's one more piece of this that gets twisted constantly, which is the idea of earthquakes triggering other earthquakes. Here is something that is true, and it surprises people. Earthquakes can trigger other earthquakes. That part is real, and it is well established. When a fault ruptures, it does two things to its neighbors. First, it permanently changes the stress on nearby faults, loading some sections while relaxing others, in a pattern scientists can actually map. That is called static stress transfer, and the technical name for the calculation is the change in Coulomb stress. Second, the seismic waves that race outward from a large earthquake can dynamically jostle distant faults as they pass through, sometimes setting off activity hundreds of kilometers away. The textbook example happened in 1992 in Southern California, when the Landers earthquake was followed, just hours later and a short distance away, by the Big Bear earthquake, a clear case of one event changing the stress and helping push a neighbor over the edge. Aftershock sequences are the same principle playing out close to home. The main shock rearranges the stress, and the surrounding rock responds for days, weeks, sometimes years. This is genuine earthquake triggering, and it is one of the most important tools we have for understanding seismic hazard. But notice exactly what kind of triggering this is. It is fault to fault. It is rock pushing on rock, energy from one earthquake nudging another patch of crust. It is entirely terrestrial, entirely mechanical, and it operates over distances measured in kilometers and timescales measured in seconds to years. Hold on to that, because it is precisely the kind of triggering that does work, and it stands in sharp contrast to the kind of triggering that does not. And the kind that does not work is the one currently going viral, because it involves something far more dramatic than a neighboring fault. It involves the sun. Right now, as all of this unfolds on Earth, the sun is putting on a show, and the timing has set the internet on fire. On the sun's disk, an active region cataloged as 4478 has grown into a large and magnetically complex sunspot group. In the technical classification, it is a beta-gamma-delta region, which is the configuration most associated with powerful flares. It covers an area of roughly 1,190 millionths of the solar disk and contains around 24 individual spots. This is a serious, active sunspot. NOAA's Space Weather Prediction Center put the 3-day odds of a major X-class flare from this region at roughly 10%, with much higher odds for smaller flares, around 45% for a medium-sized M-class flare and about 90% for the smaller C-class. And critically, the region is currently in the eastern hemisphere of the Sun and rotating toward us, which means it is becoming more directly Earth-facing day by day, more capable of sending its energy in our direction. Earlier this week, the Sun fired off an M-class flare measuring 6.8. A slow coronal mass ejection from a neighboring region left the Sun with at least a partially Earth-directed component, with arrival expected around the 30th. The high-energy electron flux around Earth climbed past its alert threshold, peaking near 1,636 particle flux units. So put yourself in the shoes of someone scrolling their feed this week. The most dangerous faults in North America are loading. Large earthquakes are scattered across the planet, and a giant angry sunspot is turning to aim straight at us. It is almost irresistible to connect them, and millions of people have. The claim spreading right now is simple and dramatic. The Sun is about to trigger the big one. Let me take that claim seriously, because it deserves a real answer, not a dismissive wave of the hand. Why do people believe it? Partly because large solar flares and large earthquakes sometimes land in the same news window, and our pattern-seeking minds do the rest. And partly because there are proposed mechanisms that sound plausible if you do not check the numbers. People point to geomagnetically induced currents, to piezomagnetic effects in stressed rock, to the idea that electromagnetic energy from the Sun could somehow couple into the crust and nudge a fault. On the surface, it sounds like it could work. It does not work, and the reason is energy. The amount of energy that a geomagnetic storm deposits into the solid Earth is many orders of magnitude smaller than the elastic strain energy already stored in a locked fault. Remember the magnitude scale. Each whole step up in magnitude releases about 32 times more energy, which means a magnitude 9 releases on the order of 1,000 times the energy of a magnitude 7. The energy locked into the Cascadia megathrust right now is staggering, and a solar storm tickling the upper atmosphere simply does not carry a comparable amount of force down into the rock. It is the difference between a hurricane and a hand fan, and when scientists test the idea directly, the correlation vanishes. Large statistical studies have taken global earthquake catalogs, going back decades, and cross-checked them against records of solar activity and geomagnetic disturbance, looking for any robust, repeatable link. They do not find one. The United States Geological Survey's standing position is straightforward. There is no established physical mechanism by which solar activity triggers earthquakes. So the sunspot is real, and it is worth watching, but for entirely different reasons. It can disrupt radio communications, it can affect satellites and power grids, it can light up the aurora at lower latitudes than usual. Those are the real stakes of space weather. Setting off an earthquake is not one of them. History makes the point even more cleanly. We have lived through far larger solar storms than anything the sunspot is likely to produce, storms powerful enough to knock out power grids and light the aurora up over the tropics, and not one of them announced itself by setting off a great earthquake somewhere on the planet. If solar activity could pull the trigger on a loaded fault, we would have a long, obvious trail of evidence by now, every major storm followed by a spike in major quakes. That trail does not exist. The connection people feel this week is built entirely out of timing and fear. And timing and fear are not a mechanism. The Sun and the fault are running on two completely separate clocks that happen, this week, to be showing dramatic numbers at the same time. There is a related claim worth dispatching while we are here. The idea that someone knows exactly when the quake is coming and a prediction is being suppressed. That one fails on its own terms. No one can predict the day of an earthquake. The hazard data is published openly by the agencies that collect it. Forecasts are probabilistic, never deterministic. Nobody is sitting on a date because the date does not exist to be sat on. So the sky looks ominous this week, and the temptation to link the flash above to the fault below is powerful. But the danger is not in the sky. The danger is in the ground, and it was there before the sunspot ever turned to face us. So where does that leave us, and what should you actually keep an eye on? Start with the honest summary. The most defensible reading of this week is that the West Coast is in a genuinely late stage of strain accumulation on two of North America's most dangerous fault systems, and an unusually visible tremor surge made that buildup legible at the same moment the sun happened to put on a show and large earthquakes happened to scatter across the globe. The sunspot is not a fuse. The global cluster is mostly the look of randomness, plus a world that now watches everything in real time. And the West Coast loading is real, slow, and indifferent to all of it. For what to watch, keep your eye on the tremor maps in the weeks ahead, because sustained or migrating slow slip is the kind of signal scientists study most closely, even though it forecasts nothing on a calendar. And while you are at it, Take the boring step that actually matters more than any of this. If you live anywhere along the West Coast, know what to do the moment the ground starts moving, which is to drop, to cover, and to hold on. And if you are near the coast and the shaking lasts more than a few seconds, to move to high ground without waiting for an official warning. Because in a great rupture, the shaking itself is your warning, and the water may be only minutes behind it. Watch the sunspot as it rotates to face us, not for earthquakes, but for the genuine space weather effects on radio and satellites and the chance of aurora. And out in the Pacific, the volcano Kilauea on the island of Hawaii is at a watch level with its summit inflated, and another episode of fountaining assessed is imminent, a reminder that the Pacific system is active and visible. That last contrast is the one I want to leave you with. A volcano like Kilauea gives us days of warning. It inflates, it rumbles, it tips its hand. The locked megathrust off the west coast may give us seconds. That is the real asymmetry at the center of this story. The trigger everyone is looking for in the sky was never the point. The fault is already loaded. The clock has already run longer than any on record. The strain is already there, waiting, and it will release on the fault's schedule, with or without the sun. The most useful thing you can do is not to fear the flash above, but to respect the ground beneath, to know that the quietest weeks are often the ones doing the most loading, and to be ready before the day arrives, because the one thing all our instruments still cannot give us is the warning we would most want. We will be tracking this as it develops.